In this article published by the Times of India in December 2023, it states that National Center for Sustainable Coastal Management found 21 out of 41 surveyed beaches in Goa to be experiencing primarily sand erosion, but in some beaches even accretion as well. So these are, you can say, prime candidates to study shoreline movements of what we are about to do. While the study was conducted for a period between 1990 to 2018, we will be focusing on a different timeline. But our area of interest, just to specify, is one particular beach of Goa, which is Anjuna beach, which is experiencing both erosion as well as accretion. To give the context of the location first, let's go to Google Maps and search for Goa. It's a tiny little state on the western coast of India. This is its location. It is bifurcated into two major territories, which is North Goa and South Goa. Anjuna beach lies on, you can say, the central to southern section of North Goa. Let's zoom into our area of interest. This is where it lies. Now for the shoreline delineation process which we'll be doing, we'll need, you can say, the area of interest in a particular file format, which is the WKT file format, or the well-known text format, which is, you can say, a reference to store the geometric and spatial information in a text format. So we'll go to geojson.io, an online tool where we can get this particular file format. There are other available methods also, but I find this to be convenient and easy to use. What we'll do is just draw a polygon around our area of interest. It is basically Anjuna beach and its surroundings. And then underneath the save button, we can just click on download WKT and it will download that particular file. We'll name it accordingly and save it in our primary work folder. Right, so we have saved this, and now let's go to EO browser once again, because just to see how that particular satellite imagery over that area of interest looks like. So we'll select Sentinel-2, and once again the atmospherically corrected product, and in the cloud coverage we'll keep it to a low amount. And in the timeline, we'll select a particular timeline of concern, which is, let's say, January to the April 2024. And we'll hit the search button. There are 3 search results. Let's click on one of them. As you may already be familiar, EO browser is a handy online tool to visualize satellite imagery. By default, the commonly used band combinations are already outlined. So true color is the optical photograph. False color is basically highlights the urban features very well. So it is mentioned that it's based on bands 8, 4 and 3. We've already used the NDWI, which is the water index previously. It is based on the band B3 minus B8 divided by B3 plus B8. Now, some of you may be wanting to know more, understand better what are these bands all about. So, Sentinel-2 is a multi-spectral satellite, and it captures, you can say, reflectances of sunlight in variety of, you can say, spectrum. So, not only visible light, but also the near infrared as well as shortwave infrared also. So, there are 13 different bands which are captured, and each has resolution of either 10, 20 or 60 meter. And the description are also mentioned, what basically captures what. Now the beauty about multispectral satellite is, by altering and playing around with certain band combinations, researchers have identified ways of delineating surface features. So we can use it to, have an optical imagery, we can create a false color imagery. Shortwave infrared basically highlights dense vegetation as well as bare soil. Geological, attributes, bathymetric attributes. So researchers have found how to basically play around with those bands to identify the surface features. So on EO browser, we also have the possibility to input our own band combination, which we determine as appropriate. So let's, for example, just use the shortwave infrared, which we saw on gisgeography.com. as you can see, dense vegetation is dark green and bare soil is brown. NDWI is also something which we can explore, and it's a index formula. It's not a composite formula. Index is, there is addition, subtraction, etc. So B3 minus B8, B3 plus B8. So it is green band minus near infrared band divided by green band plus near infrared band. So once we do that, the water features are highlighted currently in the gray shade, although we can alter the symbology to make it blue as well. Right. So there are several ways of delineating water features. So while we've used NDWI, there are several other methods also. But just to understand why we are able to do so is because water has a very starkly contrasting reflectance property than, let's say, soil or green vegetation, as you can see in this image. So in the visible spectrum, it has a low reflectance and then it basically goes blank. Whereas the others, soil, green vegetation, has relatively higher reflectances and it's basically stable across the visible and the near infrared spectrum. So this property basically magnifies, amplifies by using this particular formula. MNDWI is a modified formula which basically takes into account any reflectance from built up areas which hampers the water reading. So it's a revised formula, but then it is you can say slightly more effective than a NDWI in certain situations also. Modified MNDWI, that is. So now, I mean, the idea behind showing you this was, while its EO browser is a useful tool in terms of visualizing and obtaining and context, we actually, for this particular example, we need to delineate the shoreline. So EO browser is not sufficient for this. So we are going to Copernicus browser, browser.dataspace.copernicus.eu. This is where you can download Sentinel imagery for free. And you just, you can create an account and then search for the particular area of interest. Once you are on that interest, the filters are the same. You specify which imagery you want from the Sentinel sources, as well as the cloud cover and so on, timeline. And once you do that, the search results will appear just as it appeared in the, you can see, EO browser. So we'll use the same timeline once again. Our cloud cover is 1% because the lesser the cloud cover, the better it is to analyze the optical multispectral imagery. There are 7 results in the time period. Now, each of the products which are listed over here, it contains the date. So 2024, 04 means April, 23 means the date. And there is also time information subsequently in the product name. When we click on the product info, we'll get additional useful information, but I'm not explaining that, besides one particular factor, which is cloud cover. So the cloud cover in this particular product is 0.06%, which is very less. But then we are seeing, okay, is there something better which matches our timeline preference? So this one has again the same 0.06%. Now, if we were to see this particular product, which is from the 14th of January 2024, the cloud cover in this is really very less, like bordering, nearing 0. So 0.0007. So this seems like a good product for us. So we'll hit the download button and it straight away begins downloading. It's a slightly, you can say, large file, 1 GB file. And once it is downloaded, we can basically use it. I've already downloaded it before, so I'm not, downloading it once again. Now this was 2024. And as I have already told you sometime previously, is that for the India region from 2017, the L2A, which is the cloud corrected products, which has upper atmospheric reflectances, are available. So for the same time period as in January, we are not factoring tides and all of that, but then for the same time period in January of 2017, we have one product, and luckily for us, it has also a very good cloud cover percentage, favorable one, and we hit the download button. It's a very smooth, easy process. There was a older version of Copernicus browser before, which was again very easy to use, but the new one is much better. So I've already downloaded it before, and the files are saved in my working folder. For the next step, we will use the Snap tool. Snap stands for Sentinel Application Platform. It is a handy tool for not only visualizing satellite imagery but also processing it. It has been developed by European Space Agency, the same organization which operates the Sentinel satellite constellation. I've downloaded the latest version, version 10, and for this particular workflow, just the Sentinel Toolbox version of the software is sufficient. You can download it as per the operating system which you are using. Once we've opened Snap, we will load the downloaded satellite imagery onto the Product Explorer section. I click on File and Open and go to my working folder and click on the zipped file which I had downloaded. There's no need to extract the contents of the zip file. Snap Reader can directly read it from the contents from the zip file itself. As you can see, the product of 2024 has already been loaded. We'll load the product of 2017 as well. Instead of using the same file open command, we can even use the drag and drop feature to load the other product onto the software. Now both have been loaded. Let's explore. While there is a ton of information, we will predominantly be using the bands folder. In the bands folder, you can see Sentinel-2, which I've already specified, contains 13 bands. All of them are listed. So let's visualize the B1 band, which is the ultra blue band. Now the output isn't ultra blue in color, but it basically carries the reflectances of the sunlight in the ultraviolet or ultra blue spectrum. Besides, it has other spectrum as well, like with visible light as well as infrared. So one can see how in each of the individual bands, how the product looks like. Each pixel view in the image has a particular reflectance value associated with it. And as I hover the cursor, you can see that particular value underneath the band section of the Pixel Info tab. Now, just as in EO browser, we can visualize the imagery in some of the popular band combinations. So clicking on Window and open RGB view, we can select the MSI natural color profile, which basically inputs B4, B3 and B2 in the red, green and blue channels respectively. And the output is spectacular. It is basically the optical image for natural photograph of the satellite imagery. Now that I have taken you through the basics of visualization of Sentinel-2 imagery, we'll move to the more important aspect, which is the processing or the analysis aspect of the imagery. Now, here we will use the Graph Builder tool. By going to the Tool tab, we'll just select Graph Builder and we'll build a graph which would contain all the processing steps. Now, I will not take you through all the processing steps in detail. I'll give you a short, you can say, introduction. But then I have already written an article on this exact workflow, which is mapping water bodies using optical and radar satellite imagery. The first half of this article would be useful for you in case you want to basically understand all the processing steps in detail. You just need to search for this particular article on my website mapmyops.com to do so. So let me take you through the processing steps. It is possible for us to do each of these processing steps one by one, but then it would be too time consuming for me to show you that. There are 5 processing commands which we will add in the graph, beginning with resample, then with subset, followed by 2 boxes for band math, and finally the reprojection command. You can follow my mouse movements to know how I am accessing those commands. Once we've listed all these commands onto the graph, we'll just right click and select the connect graph button so that the order of processing is specified by us to the software. So a red arrow will link all the commands in a single graph. Underneath, we will highlight the options which we are gonna select for each of the command from the variables. So read is basically which product we are gonna process. The write is how the final product should be named. Resampling for Sentinel-2 imagery is a must because each of the band, as you already aware, are of different varying resolutions. So what this does is, by using an algorithm, it basically levels the playing field and makes all the bands with the same resolution. So our resolution which we are targeting is of 10 meters, which is the B2 resolution. So we'll select that particular option and leave the rest as default. Subset is because each imagery is 1 GB and processing it is time consuming entirely, and there's no need for doing so also, because we are just interested for a particular section within the entire, you can say, satellite imagery. We are only focused on the Anjuna beach. So our WKT file format, which we had downloaded, contains that coordinates of our area of interest. So we'll just enter it in the WKT section and hit on update. So as you can see, the red outline is of our Sentinel-2 imagery, whereas the yellow small outline is of our Anjuna beach, which the polygon which we had downloaded using the WKT format. The next command in the graph is bandmaths. Over here, we will input a formula to delineate water features from other surface features. There are several water radiometric indices to choose from. We will utilize MNDWI because it is slightly better than NDWI as it eliminates background noise. We can straight away paste the formula into the expression section. The next processing command is bandmaths2. We will rename the target band this time to CMask because this is essentially what we are gonna make. The output from the previous command bandmaths, which is the MNDWI output, will range pixel values from -1 to 1, and typically water features are between 0 and 1. So this is a binary formula where we are specifying the software that if a pixel value in the previous output is above 0, then you make the pixel value as 1, and if it is below 0, then you make the pixel value as 0. So the output of this particular command will either be a pixel value of 0 or 1, which basically delineates. So if it's a 1, then we can assume it's a water feature, and if it's a 0, then we can assume it is a land feature. So this mask is important because it kind of simplifies the entire workflow. Once we've done inputting the formula by editing the expression, we can go to the reproject command. We will transform the output from a geographic coordinate system GCS to a projected coordinate system PCS. Currently WGS84 is our GCS. We will transform it to UTM, which is our PCS. The reason behind transformation is because to display geographic information accurately on a flat screen, PCS is required. UTM zone 43 has been automatically detected by the software because that is where much of Western India, which is our area of interest, lies in the UTM, you can say, zone bifurcation. We will save our graph as CMask because that is what our final output is. We could have straight away run the graph then and there, but then I choose to close it and load the graph and then run it. Because you cannot straight away run it, you still need to verify whether all the input, output and the processing parameters are as you hope it should be. So the read is the correct product, which is the 2017 product. In the resample, we need to change because once again we need to select B2 because that is what the 10 meter resolution we want to basically normalize our entire product to. The subset command, everything is as default, we don't need to change. The bandmatch number 1 is the MNDWI command, that is also as we had desired. Bandmatch number 2 is our binary command, which basically says either 0 or 1 should be our pixel value. In reprojection, it's a software glitch basically. We need to, once again make that change from the projection of GCS, WGS84 to UTM. Once we are done doing so, everything is okay and we are now in a position to run the command. But before that, obviously we'll need to rename our product if we choose to do so, and see whether the directory is the correct one where we want to save our product. We are naming the output as 2017 January Anjuna Beach. The graph is very quick to run, although from system to system the processing speed times will differ. We can also use the batch processing command to process both the products together, but then I wish to basically show you one by one and not make it overly complicated for you, although it's frankly speaking not very difficult to run the batch processing tool also, because all the processing steps remain one and the same. Once again, we'll check all the parameters are as per our desire, and then we'll hit the run button. One thing you may have observed is in the band match section, we had named our band output as new band, which is the default only. There was one reason behind not naming it as MNDWI, because the software was taking it as a glitch because band match 2 was dependent on it. Nonetheless, we'll rename the output once again for the second product, which is 2024 Jan, and run it. Both the output are now displayed on the Product Explorer section. Let's examine the output. Once again, we'll go to the bands folder. There's a ton of bands. I don't know how it was generated, but we had only asked the graph to generate a C mask, and luckily that has been generated. So the C mask is very clear. It is basically detecting water bodies. You can see that the shape of the C mask is exactly over our area of interest. So it has matched up as per the subsetted the image as per the polygon. And all the water bodies which it has identified are white in color, and you can see the pixel value. If once I hover on the screen, it is 1. So that is what we had asked the band maths column to do, the second one that is. And all the other features barring C are all black in color. So because the location of our file is such, much of the white mask is all of the sea, and there are very tiny spots which are on land, water features. Because we don't need the other, noise, other bands which were randomly generated, we'll just delete it and save the product once again. We'll open the second product also. You can see it is one and the same. Once again, we can remove all the other bands which are not important to us and just keep the C mask band. Just to ensure that the product is updated, we will hit save button to both the outputs. Going to our working folder, I just wanted to show you that while the raw file was 1 GB nearly, the processed files are very small in size, like a few KBs only. Totally 962 KBs. So after running the graph, we have basically just extracted the information that we need, and it is very small in size, predominantly because we had used the subset command. Finally, we will now utilize another software for further processing, and for that we need to save it in a particular file format. So we'll click on the product which we want to extract, go to file, hit on export, and save it as a GeoTIFF BigTIFF format. The name of the file is the same as the name of the product, and that's okay. This was the workflow on Snap tool. Now this same workflow can be utilized on other paid GIS tools, but I find Snap, because it is free and it's very easy to use, I find it a very good medium, and it's for any remote sensing enthusiast, it's a very nice software to learn. Our next step can be done on ArcGIS Pro. It's a paid software, but luckily they have a 21-day free trial. And for certain other, processing steps, I prefer using Esri's ArcGIS Pro. Esri's GIS software is the best out there in the market, and they are kind enough to offer a 21-day free trial of their most advanced spatial processing tool, ArcGIS Pro. The processing steps of installing, I am not showing it in this workflow. It's a large file, and you just have to, hit the executable file and run it. Currently, I've already loaded it, and I'm running the software. We can create a new project, but then I've already created one by the name of Goa Shoreline. Because I had tested the workflow earlier, you are greeted to a satellite imagery base map zoomed into Anjuna beach and its surroundings. By default, you will see your software's country of registration zoomed in a topographic base map. I have dragged and dropped both the output GeoTIFF files which we had exported using Snap onto the content pane of ArcGIS Pro. It is visualized in the map view as well now. Before we proceed further, I wanted to show you an interesting anomaly. When I switch to the topographic base map, which is the default base map, and which just looks like any political physical map of a country, while the location appears to be the same, as in it is our output layer is superimposed on the correct spot, which is Anjuna beach and its surroundings. But then the superimposition is not pretty accurate, and you will get to see what I mean momentarily, when I play around with the transparency of our output layer. You see some areas which should have been marked as land pixel are appearing as water pixel in our output, and vice versa. I felt it was some processing error on my part. Perhaps both the base maps had a different coordinate system also, but none of these two hypotheses of mine were accurate. The accurate reason, in my opinion, is a subtle difference between what a coastline is and what a shoreline is. The imagery shows a standard view which depicts a shoreline, but a country's coastline is something different. To know more, read my article, the introductory section of it, which is devoted to this particular aspect. The link is mentioned in the description. When we click on any portion of our output, a pop-up appears which contains the information. So the pixel value, which is either 1 or no data value, or which is 0, is appearing. That was how we had saved the output in Snap. Our first processing step on ArcGIS Pro is to use the INT tool. It basically converts the output of a layer into an integer format. Now, you may be wondering, just as I did, our output from Snap is in an integer format. So why is the need to run this tool? I think it's some sort of an anomaly because the layer is not treated as an integer format. It is treated as a floating layer. So we need to use the INT tool once again. And the benefit of this tool is it removes all the no data values. So what you are seeing right now, the newly generated INT layer, is containing only the water pixels, and not the land pixels have all been removed from the raster layer. Let me use the symbology tool. It allows a user to alter the appearance of a layer. I'm using this tool in order to change the color of 2017 layer, which would allow me to get a visual cue of how the shoreline has evolved over a period of time. Observe the edge of the coast closely. You'll see dark blue pixels. These are actually the spots which have undergone erosion from 2017 to 2024. Our next step is to use the raster to polygon tool. Raster is a conglomeration of thousands of pixels. Currently, in our layer, all the pixels have a value of 1, which denote water pixels, and we no longer need that information. We just need the exact, you can say, shape or the location of the water body, which will help us in our subsequent workflow of delineating the shoreline. So this particular tool converts the raster layer into a polygon shape, which is the form of a vector layer. I'm keeping the simplify polygons and create multi-part features option selected because it is suitable for our particular workflow. Both the layer outputs have been generated. I'm choosing to symbolize it in a different way rather than having colored fills. I'm just choosing to keep an outline of the shape because the entire layer no longer comprises pixel values. It's just a singular shape. So if I click on any portion of the shape, you will just see one attribute which contains the length and area of that particular shape. Even in the attribute table, you can see the length and area, and one attribute is mentioned. This is the utility of this particular tool. Now that we have converted our layer into a vector format and into a polygon, we'll proceed to the next step, which is to convert the polygon shape into individual lines, and then we'll subsequently extract the shoreline adjacent to Anjuna beach. We'll enter the input layer and the name of the output layer. It's a very simple tool to run. Likewise, we'll replicate it for 2024 layer. Using the symbology tool, we'll just alter the color of 2017 into a dark red shade. So this is the new layer which contains lines. So when I click on the layer, it will not select the entire shape. It will just select a bunch of contiguous points, or you can say individual lines. So the line which has been selected on your screen right now is actually the line the shoreline adjacent to Anjuna beach, and this is what we are interested to keep. So we need to extract this particular line from the generated layer. In the attribute table, our selection is demarcated. It is row number 39, and we will need to keep this particular row. Observe that it has a shape length of 5.6 kilometers. So intuitively, what we want to do right now is remove all the other rows and just keep row number 39. That is what we are going to do. We are left with just one row, and we'll hit the save button, not the save project file, but under the edit tab, there's a separate save button. We'll have to click on that so as to save the edit to the attribute table that we have made. And now the layer does not comprise of multiple lines, just one line. Switching over to the 2024 view, you can see that it's not the exact replica of 2017. Now the current selection selects not just one line on the coast side of it, but even on the sea side of it. So it's basically a series of contiguous points. So we need to manually attach a break line in order to delineate the shoreline which we want. So how do we go about doing so? So first, let me open the attribute table. You can see that there is one large line which corresponds to our selection, which is 14 kilometers in length, and we don't want that entire line. So the way to create that manual break is by using the split command in ArcGIS Pro. Under the edit section, you can go to the split command, and all what you need to do is manually crisscross that section which you want to keep. So it will break that particular section of line away from the main shape. Observe that there was a blink on the screen at the area where we wanted to keep the break. Observe it once again as I am entering a break line. Yes. So now what has happened is it has delineated that particular shape from the entire shape. So once we go to the attribute table right now, we'll be able to see that the new shapes or new lines have been created. So instead of that 14 kilometer line, we now have 2 kilometer line, 8 kilometer line, and so on. So right now we just have to select the line which we want to keep. There are two lines which we want to keep, and we'll have to observe what is the length of that. Intuitively, we'll go to the attribute table, and what we'll essentially do is just keep those rows and remove all the remaining rows. The largest line still corresponds to the seaward facing boundary of the satellite imagery. We don't want to keep that, but the remaining line we will, the next two lines we will keep. Once again, we will click on the save button in order to save the changes we made on the attribute table, and this save is under the edit tab. Now the objective which we had is finally achieved. We have identified the shoreline in 2017 and 2024 respectively. We've done several processing steps across spanning couple of softwares, and the output is there for us to see and explore. It gives us an indication where accretion has happened and where erosion has happened. So 2024 is yellow colored and 2017 is red colored. So where the yellow color is facing more towards the land, it essentially means that the area has undergone accretion, as in new land has been added. New, you can say, sand has been added, and we can even use the measure tool to get a rough area of where erosion, what is the, you can say, the length of the erosion or the accretion which has occurred, and even the area. So such basic calculations one can do. This is a rudimentary way. I mean, this particular extracted shoreline we can subsequently use in more advanced workflows, which we'll see in one of the later example. But then right now what you are essentially seeing is how the exact shoreline has evolved, and this is not a foolproof technique. There are certain drawbacks of it, but it's a good you can say way of doing a this is the first time actually where we have extracted a coastline, a shoreline basically. There's one more aspect which I wanted to show to you in EO browser, and this is useful. So if you remember, in Snap we had made a binary function that if above 0 then make it 1, which is a water pixel, and below 0 then make it 0, which is a land pixel. Now the way 0 was identified is by years of research by scientists and researchers who had identified that using MNDWI or NDWI function, 0 is, you can say, the threshold where the land basically differs from sea, but that's not always the case. It's basically an approximation. So what happens, what I'm doing right now is basically saving the views. You can see right now the true color composite of the view is being depicted. What I'm doing is I'm adding that particular view to a compare cart, and similarly the NDWI view of that particular location, I'm just adding it to the compare cart. So we've added two layers. One is the true color layer and one is the NDWI layer. Now let's create a modified NDWI layer, which is B3 minus B11 divided by B3 plus B11, and we will save this particular visualization also as our third layer in the compare cart. We've altered the symbology, so the blue areas are the areas which are water body. Now the reason behind showing you this particular, you can say, feature, it's a very useful feature. So what you can do is, while in this particular case it's not very evident, but then you can see among the two layers. Let's say you want to choose between NDWI and MNDWI. You can see which of these layers correspond accurately to the coastline. That is what you can basically see. Besides that, if you can also modify the threshold. So let's say you want to, instead of 0 as a threshold between land and sea, you want to keep a different threshold, let's say a higher threshold, 0.1, and to see how it basically, whether it mirrors the border appropriately or not. You can actually do that, make that change, and the correct way of doing so is using the histogram function also. So let me show you the histogram function right now. So you can see there are two peaks. So there are two distinct peaks. The negative peak is for the land and for the positive peak is for the water body. And you can see where the break is and then determine which pixel value should be the right threshold. And you can use that as a, you can say in the formula in Snap, you can use that particular value instead of a pure 0 in order to make the correct approximation of the shoreline. Once again, this particular thresholding feature is more suitable for detecting, minor water bodies and not for, big seas and oceans. But then certainly it is a useful aspect for you to know, and it could prove decisive in selecting the right water radiometric index as well. So I hope you enjoyed this example of extracting a shoreline by utilizing Sentinel-2 imagery, we've used the Snap tool as well as the ArcGIS Pro in order to do so.